Hi, my name is Polonati Balaji Sandeep, and I am final year BTech student from Department of Electronics and Communication Engineering. Today I am going to present my Embedded System Internship project by Emertxe. The title of this project is Real World EV and ADAS System to Build. So by using the STM32 F103C86 and PicsimLab. The main objective of this project is to simulate the electric vehicle control system with advanced driver assistance system feature using the STM32 microcontroller. The project includes UV parameter monitoring, obstacle detection, collision warning, blind spot detection, fault handling, and real-time Python dashboard for visualization. So we see this PPT, and for this project, challenges and proposal solutions. Current EV challenges proposed system. So current EV challenges based on the in real life water present have limited driving range and battery management, battery issues, and collision risks, and blind spot accidents are also happening. Motor overheating issues. Overheating is main current challenge in real life in present time. So in this project, how we overcome from these points. So we propose in the proposed system we see what a real project we will do. Real-time EV parameter monitoring, obstacle detection using ultrasonic sensors. By using sensors, we detect the collision before blind spots and ADAS features and fault detection and safety monitoring and Python dashboard for visualization. And the requirements are two types, hardware requirements and software requirements. And hardware requirements are we use in this project so that STM32 F108 103C8T6 Blue Pill microcontroller and potentiometers. In the potentiometers, we will see acceleration, brake, SOC, and motor temperature. And the ultrasonic sensor we used in this project is HCSR04. That ultrasonic sensors are we took three that are for front, left, right, and LEDs are collision, blind spot, and fault indicators, and virtual terminal in PicsimLab. So in software requirements, we see STM32 Cube IDE, PicsimLab, Python, and VSPE, and Teraton. The tools required as we see in requirements. So these are tools required: STM32 Cube IDE, PicsimLab, Python software, VSPE, and Teraton. So basically, STM32 Cube IDE is a software integrated development environment IDE. It is a STM32 microcontroller and used to configure the STM32F103C8X. It is a Blue Pill microcontroller. Peripheral settings are configured using .ioc file. And in that .ioc file, we see the pin configuration. Application code is developed in the generated source files. And the project compiled and debugged to generate the executable binary file in .bin file. The generated binary file is loaded to PicsimLab for simulation and testing. Then we can see the which we run the code that it is simulated in the PicsimLab by using .bin file. PicsimLab is simulation platform that executes .bin file as I said before. It acts as the target platform STM32F103C8X and that Blue Pill microcontroller. And the generated binary file is located into PicsimLab for simulation. It provides virtual components such as potentiometers. In the potentiometers, acceleration, brake, that SOC and temperature that we can change. Ultrasonic sensor for detection. Collision occurs for ultrasonic sensor. LEDs to fault and buzzer, and input output virtual terminal to see the which in the parameter potentiometers what we changing, and based on that in virtual terminal we can see the STM32F108 C86 microcontroller is based on the ARM Cortex M3 processor. Peripherals are connected according to STM32 pin configuration. The IO virtual terminal displays the real-time UART output to verify the project. So we see the result in PicsimLab after we executed the program in STM32. So ARM Cortex M3, it is a processor, 32-bit processor used in STM32F103 C86 microcontroller. Provides high performance with low power consumption. It supports peripherals such as ADC, timers, UART, GPIO, suitable for real-world embedded applications like EV and ADAS. So we use it in this project also. And GPIO, general purpose input output. The GPIO is used to interface external devices like with the STM32, configured as input output or analog mode depending on the application. In this project, we see GPIO is used for LED control. When ultrasonic sensor collision occurs, then fault and red light is red LED blinks like that. We used fault and blind spots indicator LEDs. The block diagram of EV and ADAS system. So potentiometers in that acceleration, brake, SOC, motor temperature, and STM32F103C86 Blue Pill. And ultrasonic sensors have three, and those are front, left, right, and the UART communication for virtual terminal, and to also Python dashboard. This is the block diagram. So EV parameters are, as we see in Python dashboard, are these reads analog input from potentiometers like acceleration, brake, SOC, motor temperature, converts analog input into digital values by using the STM32 AD analog to digital converter. So calculates the EV parameters such as speed, torque, battery SOC, range, and also temperature. Implements regenerative braking, where braking decreases speed and increases battery SOC. Supports three driving modes. Those are normal, eco, and power. ADAS parameters monitors left, front, and right obstacle distances. Provides forward collision and detects left and right blind spots also, and calculates time to collision and generates warning and critical alarms. This detects a system fault conditions also. So basically UART, it is a serial communication interface for data transmission. So transfers EV and ADAS data from STM32. Sends real-time data virtual terminal. It acts as communication. So it communicates with a virtual terminal and Python dashboard from the STM32. Basic project to understand STM32 Cube IDE and PicsimLab. This is the first project which as a sample project which we done. It is LED blink project. So first I will show you the project. Let us see into the project. So this is the LED blink project. First I will run and check. Yeah, this is zero errors. Now I show you the output in PicsimLab. So in the PicsimLab, we will add the .bin file. So here I am loading .bin file. This is the project folder of mob blink, LED blink. So we load the .bin file. Here we can see LED blink is happening. So this is the first sample project when I was done earlier of this project, EV and ADAS project. So now I am closing this project. Okay, this is reading potentiometer values. So a potentiometer simulate acceleration, brake, SOC, and motor temperature as we see before. So analog voltages are read through the pins are PA0, PA1, PA2, and PA3. The STM32 analog digital converts analog signals into digital values. The I/O input output version terminal displays the real time sensors, and the processed values are transmitted through UART. So the communication with the UART. So here we can see the block diagram. These are potentiometers, a accelerator, brake, SOC, and motor temperature, which are connected to STM32 and UART communication. Here we can see, and these connected to virtual terminal. Here what it displays the real-time sensor values. And potentiometer, we are variables resistors used to generate analog voltage. Output voltage range 0 to 3.3 volts are connected to the STM32 ADC input pins. Simulates acceleration, brake, SOC, and motor temperature. Provides analog input for EV parameter calculations. Yeah, here analog to digital converter, and therefore the measured acceleration, brake, SOC, motor temperature, analog values are converted into digital values. So here in STM32 the ADC is 12-bit ADC 0 to 24095. That the formula we used in this is it is so V in by V reference into 4095. Here 4095 is the maximum value. To calculate it is V in equal to ADC value into V reference by 4095, and V in when it converted to ADC value it is 0. When V in 1.65, ADC value is 2047. When V in we took 3.3 volts, then the ADC value is 4095. Scaling for ADC values. After reading the values from ADC, the STM32 will scale them as acceleration 100 and brake 100 and SOC also 100%. Temperature is 150%. Ultrasonic sensors it measures the distance between vehicle and nearby obstacles and uses two signal pins. These are trigger and echo. The trigger pin sends 10 microseconds pulse to start measurement. The echo pin remains high until reflected pulse is received. Distance is calculated using echo travel time. The distance formula here we can see speed of sound into time by 2, and distance is 0.0343 into time in microseconds divided by 2. As we can see in block diagram, here it is a sensor, and in sensor trigger pin, echo pin we see, and trigger pin it sends 10 micropulse to start measurement, and with when object in nearby, then echo pin remains high until reflected pulse is received. In this block diagram we can see. Yeah, timers is one major peripheral in our microcontroller. It counts time. The internal frequency of Blue Pill board is 72 megahertz. If we divide 72 megahertz with 72 hertz, we will get 1 megahertz. Then clock value is 1 microsecond. The timer count will increase for every 1 microsecond. So here we see clock 1 by 72 megahertz PSC plus 1 into error plus 1. Now we see. Yeah, EV control calculates EV parameters such as speed, torque, battery, SOC, range, motor, temperature. Acceleration increases vehicle speed and torque while reducing the battery SOC. Braking decreases and enables regenerative braking, which helps the increase battery SOC. Supports normal, eco, and power driving modes to control vehicle performance and range. Uses predefined vehicle parameters such as vehicle weight and threshold values for EV calculations. The calculated EV parameters are updated periodically and displayed on the input-output virtual terminal and Python dashboard. Distance reading. Here we read the front, left, right distances by using ultrasonic sensor. By using three ultrasonic sensor, we all read the distance from for every 100 meters per second, and the maximum distance measured by ultrasonic sensor is 400 centimeters, and the left right it is less than 30. These distance are increased printed on the input output virtual terminal, and by distance we calculate time to collision TTC. Forward is less than 230 and left right is less than 30. Alarms, time to collision is equal to distance by time. According to time to collision, we have alarms, warning, critical. If TTC is less than 3 seconds, we will show warnings. Alarm, the distance is less than 50 centimeters. If TTC is 1.5, we will show critical alarm. Two alarms we have advisory, speed is high, and no alarms are there. Here we find blind spots in left and right. If sight distance is less than 30, the blind spot LEDs will glow. These are the types, that is red color critical, left, blue color is left, and green color is right, and yellow is fault. First some final state mission. Here we will observe different states that vehicle is undergoing. The conditions for state also vary. The states we have are parked, ready, driving, regenerative braking, fault. When the acceleration of the vehicle is above 2%, then the state of the vehicle changes from ready to driving state. When the brake is applied, vehicle changes it from driving state to regenerative. Brake is greater than 5%. When brake greater than 5% and the brake is less than 5%, then vehicle again enters into driving state, fault, and vehicle should enter into fault state from any state. First some flow chart here. When parked the vehicle when ready, acceleration is applied, then driving. When driving, brake applied, regenerative braking, and regenerative braking, brake released, then driving. These are when all these happening in between, then fault is applied. Fault is happen when these conditions are going. Fault. The system continuously monitors critical vehicle parameters. A vehicle state is activated when an abnormal condition is detected. Fault conditions include low battery SOC, high motor temperature, and collision detection. And the vehicle enters into fault state to ensure safe operation. The fault status is indicated using yellow LED before we see in LEDs. Shell process. The shell process enables communication between the PC and STM32 controller. Through UART, this is used to send the commands and receive the diagnostic information. The IO input-output virtual terminal acts as the user interface for entering commands. The STM32 processes the received commands and performs the required action. The execution result is displayed IO virtual terminal and Python dashboard. As we can see, STM32 control unit here, and UART, it is communication in between the input output virtual terminal, and also here Python dashboard. Teraterm and VSPA. Teraterm is a serial terminal used for UART communication. It is used to send commands to the STM32 control unit. It also displays system responses and diagnostic information. Common commands include help, speed set, mode, fault, clear. In VSPA, it is a virtual serial port emulator. VSPA creates virtual COM port connections between applications. It enables the communication between STM32 simulator and Python dashboard. It eliminates the need for physical serial cable. For example, Here, here comp 4 to comp 1. Python dashboard. We see in the Python dashboard provides a graphical visualization for real-time EV and ADAS data. Data is received from the STM32 through UART. It is displayed and easy to understand the format. The dashboard includes a speedometer and battery state SOC, EV metrics like torque, acceleration, brake, motor temperature, ADAS bird's eye view, and speed history graph. The speed of the graph, it will show some alarm and fault status. Here we can see the EV dashboard. Now we see pin configuration. Yeah, here is the pin configuration. We'll see the pin configuration here. Here is the pin configuration. Now I will open the main.c. Yeah, here is the main.c, and these are all the .c files, and these are the header files. Now in the main.c, here we see the main project, main.c project. We can see now we will run this project. So no errors. Okay. Now I'll, yeah, this is the STM32 cube ID. Now I will show in PicsimLab. Here is the PicsimLab. This is a blue pill. What I said before. And now these are the spare parts. Yeah, here spare parts. Yeah, this is the potentiometer, and these are the sensors, and this is the LEDs, and this is virtual terminal, and here is the buzzer. In the potentiometers, we will see the accelerator, which is the first one, and the second one is the brake pedal, and the third one is SOC, and fourth one is a motor temperature. Here these are connected PA0, P1, PA1, PA2, PA3. So these are the sensors, and these are the distance which we can change these for 3. And these are the LEDs for collision, blind spot, left, right, and fault. And this will show the data which we see in this, and that will show in the virtual terminal. Okay, now first I will load the .bin file. Here .bin file load, and my provide here .bin. Yeah, now I load .bin file. Now I will open this virtual terminal. Once I will reset. Now I will see you. Yeah, you can see in the virtual terminal the speed, SOC, torque, temperature, range, acceleration, brake. And here in the down, front distance, left distance, right distance, time to collision and collisions, and blind spot, alarm, and fault. So this is the speed by which we increasing and decreasing, it will show here. And this is the SOC battery percentage, and torque, it will show the temperature of the motor, and range also it will show here, and acceleration which we increase it and decrease it. And here is the brake. Okay, now I will show you by increasing the speed. By increasing the speed, and SOC set to full, and now we'll see the speed will be increasing. Yeah, we can see from initial 22, and we will see the speed here 22, like this speed is increasing. And we'll see the distance, the center sensors. Now I decrease the sensors. See, you can see fault. Here you can see fault and also collision. When I reduce the distance of the front sensor, you can see here 53, 55, it is reduced. So here also you can see in the LEDs, it is showing fault and collision. Now it is increasing. See, now it is gone. And now we'll see for the same as the left. Now I'll set to less than 30. It will shows 20, which is I set to 22. It will showing 20. It has related. And now in blind spot left, it will show you blue color. And now I set back and it was gone. Now I will show you the same as to right also. Now I set less than 30, it's showing green in the LED. Now I show you in this virtual terminal. So here you can see range, right distance is 30, 10, sorry 10. Yeah, here you can see in LED also. Now I set back it normal. And these are the LEDs. Here now I apply the brakes. So now I apply the brakes. I will open virtual terminal. Yeah, I was in virtual terminal. You can see when I brake applied, here torque will get negative. Here torque negative and SOC will increase regenerative braking. Okay, now I will show you the VSPA. So VSPA, here is the pair COM10 and COM11 which I made. So I made the pair as COM10 and 11. These are the pair. Yeah, here is the speed and here is the speed graph and here is the battery and here is the alarm, which if any alarm is critical then it will show here. And these are the EV metrics, torque, accelerator, brake, motor temperature, alarm, fault and signal. The mode is normal and range is range also showing here. This is the range and here is the shows if any obstacle in from front or left or right. Now we will see by decreasing it. Yeah, by decreasing the sensor of the front distance, we will see. Yeah, here blinking collision and fault. Now I will show in Python dashboard. Yeah, you can see here. You can see here critical alarm and it is also red color from the front distance. When we decrease the in the sensor, it will shows the critical alarm. Now I set back it to normal. Now you can see there is no alarm, none. So here is normal. Now I set left one less than 30. Then you can see here a blind spot for left. Here is blinking blue color. Now I will show you. Yeah, you can see here from left advisory, alarm advisory. Left it is showing. Now I set back to normal and now I put the less than 30 to right sensor. You can see here LED is green. So here is the blind spot from right. And now it is shows in, yeah, you can see here right distance, right one blind advisory. It will shows the alarm advisory. I set back to normal. Yeah, here now we can, yeah, now we can see here alarm none So no obstacles are near the vehicle. So alarm none. Now speed is also increasing to 31. Now we'll see by applying the brake, we will see what will happen. So here we can see brake is applied 21 percentage. It is also showing. Now we set back to normal. Now we can see brake is 0 percentage. You can see. And motor temperature also here you can see. See here motor temperature changes 46.8. Yeah, you can see. Yeah, this is the project of EV and ADAS vehicle system. This is the Python dashboard of that. And thank you.